All right, well, welcome everyone to this new seminar on the series of seminars that we have in the PhD program in aerospace engineering. Today, Manuel Soler is away from office, so I'm in charge of introducing our guest and speaker. So let me introduce you to Dr. Luis Chacon. Dr. Luis Chacon is working at Los Alamos National Laboratory as a senior scientist in the theoretical division over there. He has been the recipient of the Ernest Lawrence DOE Award in 2021 and is also a fellow of the American Physical Society since 2020. Luis has studied here in Madrid at UPM, where he graduated as industrial engineer in 1994, and then obtained his master and PhD degrees in nuclear engineering from University of Illinois. He has also spent some periods of time at Oak Ridge National Laboratory, and well, his publication record is very impressive. 128 publications. Has been cited more than 4,600 times, and he's been working mainly on algorithm development in fluid and kinetic modeling of plasmas, okay, for applications such as nuclear fusion of inertial or magnetic confinement. And nowadays he's visiting us for this week because he's collaborating with the EP2 research team on developing a new implicit particle in cell code. Okay, so that's the line where we are working together. He has organized numerous conferences and workshops in his field, and well, I would think that it's an honor for us to have him here and be collaborating with us. Okay, so Luis, all yours. Let us have his talk first, and then we'll have some questions as usual. Okay, thank you.
Thank you. Thank you, Mario, for the invitation and for the kind introduction. This is probably too long a talk, so I'll have to shorten it as we go. I've been told 30 to 40 minutes, so I'll try to stick to that. But it's summarizing work happening over the last 15 years or so. Actually, some of it starting at Oak Ridge while Raul was there as well. And actually, we talked about some of the stuff that we eventually did here. So it's been a long while, and I'll talk about, if I have time, both magnetic fusion as well as inertial fusion. They have very different challenges, and we developed very different technologies for either. So this is not work that I've done on my own, obviously. There's plenty of people that have collaborated over the years in the work that I present, some of them as postdocs and then as staff members. Others as senior mentors and advisors. So I'm indebted to all of them. And of course, the support of several agencies over the years, including Oak Ridge, Los Alamos, and DOE. So just to frame the talk, it's really a great time to be working on fusion. 2022 was a record-breaking year for ICF. This is inertial confinement fusion. Is the one that we'll describe it later. You shine lasers on a pellet and you compress it and it ignites. And the laser input in particular is 2 megajoules, give or take. And the neutron yield was several 10 times to the 17. The energy deposited in the capsule, because it's an inefficient process right now, is 250 kilojoules, and we produce 3.15 megajoules out. Which corresponds a gain of 10 versus the energy on the capsule and 1.5 what we put in the laser. So this actually surpasses all criteria for ignition established by the National Research Council in 2007. So it's a very big deal. 2021 was also a really good year for magnetic fusion. JET actually doubled the energy in a single shot and extended the shot by about 30 times. Which was the longest shot on record, and sort of demonstrates sustained, quote unquote, because still it's only a few seconds, but compared to the timescales of the plasma, it's a very long time in a tokamak device. So this is what I'll cover if I have time throughout the talk. I'll introduce plasmas and fusion and confinement approaches, the main ones, the 2 main ones, and the challenges to simulate those systems. And then I'll go into particle in cell on one hand, and the application to magnetic fusion energy, and multi-scale methods for blast of Fokker-Planck on a mesh, actually, and applications to ICF, inertial confinement fusion, and then I'll summarize. So let me begin with thermonuclear fusion. It's the process where, if you reach enough temperature and densities, the lighter nuclei combine to form heavier ones and converts tiny amount of mass into a lot of energy, according to Einstein's mc² formula. And it drives the birth, life, and death of stars in the universe, and therefore of life on Earth. In stars, matter is confined perfectly by gravity, can go anywhere, and that's what allows for long-term fusion to happen. But in the laboratory, the challenge is confinement, because you need to confine matters that's very, very hot. And that's the key. So it's attractive because fuel is inexhaustible, geographically distributed. You have only a small amount of fuel, so you can shut it down very quickly. It's inherently safe. It cannot run away from you, but it's hard to do. Eventually, there'll be no harmful radioactive or CO2 emissions, so no global warming. And even the first generation fusion reactors will activate structural materials because there will be neutrons, but the hope is that the future next generation fusion reactors will be neutron free. And this is just a Wikipedia piece of information. 100 kilograms of deuterium and 150 kilograms of tritium is enough to operate a 1 gigawatt electric power plant for 1 year. So what is that is required to fuse matter and hydrogen isotopes in particular? 100 million degrees, give or take. That's enough energy to overcome the electrostatic repulsion of the atomic potential, nuclear binding potential. And at such temperatures, the matter is ionized and is a plasma. That's the fourth state of matter, which is actually the most common in the universe. It is so hot that it will melt anything, so it cannot come into contact with any reactor vessel or any material, really, if you can avoid it. And that's where confinement is key. So how do you confine it? Right now, there's two main ways. One is with magnetic fields, and the magnetic field confinement rests on the principle that if you have a plasma, which is a ionized, matter with electrons and ions going every which way, if you put a magnetic field on that, then all of a sudden those charged particles gyrate along the magnetic fields, and they can only really transport themselves along the fields, right? And if you now turn that around and make it into a donut, a torus, then you can in principle avoid end losses and therefore make a suitable confinement device out of it. It's not as easy as this. Turns out when you do that, the plasma still features collective effects, instabilities, and a number of other things that can ruin your confinement, but that's the principle of it. Or you can compress it by compression. That's the other option, and that's what inertial confinement does. I'm showing here pictures of a pellet, which is about 1 millimeter in diameter. And then on the right is a whole round, which is a cylindrical metallic device that contains the pellet that's shown with lasers. And in the process, that energy gets transformed into radiation that bathes the capsule. And what happens is the outer matter evaporates, rocket effect, compresses the capsule inward, and if you do it right, you can achieve densities and temperatures that are suitable for fusion. And that's how that ignition result that I mentioned earlier happened. And the magnetic confinement is actually based on tokamak devices, which is also what I mentioned. So this is what we're actually doing today. Now, if you look at plasmas in nature, in terms of density and temperatures, you find out that these laboratory plasmas are actually in extreme conditions. And this is what makes it so hard technologically to achieve. All right, so what set of equations described this system? It's called the Fokker-Planck-Maxwell system. And again, fully ionized plasmas is a soup of ions and electrons coupled by electromagnetic fields. So the equation that describes those particles is actually it's called the Fokker-Planck equation, which has a transport component right up here that actually has velocities and accelerations due to electromagnetic fields and also collisions. All right, the particles collide with one another, in this case with Coulomb collisions, but you may have also collisions with neutrals and collisions, mostly with neutrals. So Coulomb collisions and collisions with neutrals that you may need to model in this system in order to capture the physics. Coulomb collisions are described by the Fokker-Planck-Landau equation. We'll look at that a bit more carefully later. It's a very difficult equation to solve. And that's coupled with the Maxwell's equations, which we know well, and that they're driven by current densities and charge densities, which are in turn found from the distribution functions of the particles, which I should mention are 6-dimensional. You have physical space and you have velocity space, which depends on the velocity coordinate v. And so this equation in the yellow box is actually 6-dimensional plus time. So a very high dimensional system. And these equations have constraints. F is a probability distribution function, so it has to be positive. Should conserve mass, momentum, and energy. It should feature an H theorem, which means the entropy always increases. And it is extremely rich asymptotically. You can derive many subset models from this one, assuming certain asymptotic limits that give you reduced models that are really very useful to simulate many of these systems. You have quasi-neutrality, which is the charge balance and bipolarity, multi-fluid, where you assume collisions are frequent enough that you can assume a local thermal equilibrium, in which case this F is a Maxwellian distribution function, and then you can go from there to resistive MHD, ideal MHD. This is a hierarchy of models that are now currently used, actually, to simulate these systems, to target specific phenomena that is actually suitable for the assumptions that you've assumed. But if you look at it from a first principles perspective, the problem is you have all these scales in time and space that are present in these systems. And I'm showing here for magnetic fusion, the scales go from 10 to the minus 10 seconds to 10 to the 4, so 14 orders of magnitude. And you have various phenomena along the way that matter and that you need to model carefully, right? And people derive specific descriptions for these, right, in order to make progress. But if you want to do something first principles, you really need to be extremely clever. Similarly, in space, you have a range of length scales, in this case 10 to the 8, that go all the way from the gyration length scale that I mentioned earlier to essentially system sizes and collisional mean-free paths. So, this kind of underscores the challenge of simulating these systems. It's all about multiple scales. So we need to exploit the model hierarchy that I mentioned earlier in order to make progress. And one important idea is to use this nested set of models to accelerate the higher fidelity ones. And that's why I say here fluid moment-based models to accelerate kinetic simulations. This is an old idea, actually, started in 1967 at the old ERS by Golden in thermal relative transfer. And then it was actually explored by people in the US, Brightville and Mason, particularly at Los Alamos, with, they call it implicit moment method. It was a linear model, algorithm. We've now actually extended that non-linearly to both magnetic fusion and inertial confinement fusion, and I'll show some of that here. And the key idea, again, is that the moment system of equations, which is the fluid equations, can be used non-linearly to accelerate or linearly to accelerate these higher fidelity kinetic descriptions. Okay, and I will present examples for both magnetic fusion and inertial confinement fusion if I have the time. All right. There is going to be an emphasis throughout the talk on conservation properties. This goes back to the structure of the equations that I mentioned earlier, and I'll show examples of what happens when you don't get those and how bad it can be. So let me start with the application to magnetic fusion and in particular particle methods in that context. And again, the Vlasov equation is what governs the behavior we're interested in. I'm going to assume the collisions don't matter. Eventually they do, and you need to have a solution for that, which a lot of people have worked on, including ourselves, but I won't talk about that today. And that couples with Maxwell's equations through the moments. Okay, and this is, I should mention, a singular limit of the full Vlasov-Fokker-Planck, including collisions, in that the Vlasov equation features an infinite number of invariants, but only mass, momentum, and energy survive when you add collisions, so those are the ones that we're going to focus on. So the particle method is basically a method of characteristics where you know that the Vlasov equation actually has this type of solution. If you know the initial particle positions and velocities, you can essentially solve for the characteristics along the way, and then you find the solution at all times. Of course, the characteristics depend on the electromagnetic field, so you need to couple with that, and that's how you need to time step and so on. What people use is particles or macroparticles, which are volume in phase space. It's really a Green's function method at its core, but people intuitively think about particles as physical things. And the way that it works is you basically describe the distribution function using delta functions, which are the particles. They obey equations of motion, in this case, Newton's equations of motion. You could also have the relativistic equations of motion here if your regime is such that you need them. And then these move through the mesh, where the mesh describes the fields, and the fields are discretized on the mesh, so Maxwell's equations, right? And again, you have to couple through the densities, charge densities and current densities to evolve the fields, and you find those by gathering moments from the particles to the mesh through some kernels. In this case, they're called B-splines. Okay, and you find the fields on the particles from the fields on the mesh with those interpolator functions, and similarly the moments on the mesh from the particles using the same interpolation functions. So this is a very simple method, actually, and its implementation is pretty straightforward, and it's been working as a workhorse since the 60s, basically. And the original classical algorithm is really simple. You iterate in time, where you start by weighting the fields on the particles to find the force. You move the particles to find the new positions. You find the moments on the mesh from the particles, and then you update the electromagnetic fields, and then you keep on going. Okay, very simple. And the velocity and position is targeted in time, like described here. This is called leapfrog, because it seems like a frog jumping over one another. It's a very simple method. Okay, that's not what I want to do. All right. So very straightforward, but it has limitations. And the limitations that it has is that it's unstable if your time step is too large. And actually, it's also unstable if your mesh spacing is too large compared to the characteristic length scale of the system. It's called the Debye length. And it doesn't conserve energy. And what happens is, as you start simulating these systems, the energy starts growing, and then at some point, your simulation is nonsense, right? So this is what's called an explicit time marching scheme. Implicit time stepping, actually, when you solve positions and velocities and fields at the same time and you iterate, may actually solve a number of these issues. And people actually started looking at this since the 80s with two schools of thought. And both of them were linearized and semi-implicit, meaning you didn't really converge non-linearly on the system, on the original system. And that led to significant inaccuracies that in turn led to self-heating and cooling, so you didn't get anywhere. However, when you actually do nonlinear with exact conservation properties, you get somewhere. And that's exactly what I'll describe in a second, including the ability to use fluid schemes to accelerate. All right. So this is the Vlasov equation discretized in time, not in velocity space or physical space. And this is essentially here to illustrate the complexity of an implicit coupling. What it means is the field, in this case the potential, is coupled to the new time distribution function, which in turn is coupled to through the potential and new time via the acceleration. So it's a fully coupled system that you need to solve. And if you describe this with particles, when you end up with a set of equations that has the field equations on the mesh, but also the particle equations, and the particles could be billions. All right, so this system is so large, you cannot probably put it in the computer. As such. So this is a no-go if you try to do this, in the straightforward manner. But that's not what we do. If you realize that the positions of the particles and velocities of the particles actually can be found independently once you're given the potential, you can actually express this as a functional in such a way that in the end, the set of equations you need to solve depends only on the fields. And this is a critical realization because the fields are macroscopic, they kind of relate to fluid moments, and they also are 3D. So all of a sudden, something that was, an impossible system to solve becomes completely tractable. Okay, it's now the requirements are far lesser than they were before. We have ways to solve these systems once formulated. I'm not going to go into the details here. In this case, I'm showing here Newton's method, which is a very well-known technique of linearizing and then iterating. But there's a number of advantages here that allows us to use modern iterative techniques that allow us to not form a Jacobian and allow us to actually precondition, which is essentially use an approximate formulation of the system to accelerate the original one. I'm not going to get into the details, but the point is this preconditioning idea is exactly what we're going to exploit to use fluid models to accelerate the fully kinetic system. All right. So now I'm formulating a discrete electrostatic Vlasov-Poisson or Vlasov-Ampere system here, where I'm highlighting the implicit couplings throughout. This is just Ampere's equation, the position update, the velocity update, and the current gather. and they're all coupled throughout. But it turns out if you formulate it exactly this way, you can prove in one line that this conserves energy. Whereas before we couldn't, now we can. And this changes the game, because now instead of having this self-heating, as I mentioned, throughout the simulation that ruins your simulation, that cannot happen anymore, provided you converge. Okay? You can do more. The fact that the particles are now what we call enslaved, because we eliminated them from the residual, they're just operations that we do once we have the fields, allows you to do fancy things with them, including subcycling if you need to. And among other things, it allows you to now conserve strictly charge. Another one of those conservation properties that you had better satisfy if you want your solution to mean anything after a number of time steps. So we can subcycle along a given orbit for a given outer time step, whatever that is, to make sure that we conserve charge, but also to make sure that our orbit is properly integrated. So now you can build in accuracy in that integration. And in the outer iteration, you don't see that process, and it doesn't really affect your convergence very much. You can recover your energy conservation once you do that too. There's ways to orbit average the moments in a way that the same proof follows through. So you do not spoil the conservation properties that you had. And it matters. So this is a simple problem. It's an ideal acoustic standing wave. With electrostatic, Vlasov-Poisson is one of the few multi-scale problems you can do. And what I'm showing here is 4 solutions. The red one you can consider truth. The others are solutions that violate some of the things that I mentioned I could do. So I don't subcycle, or I subcycle without really checking the accuracy, or I take too much a time step, without subcycling. All of those end up giving me an answer that's wrong. Okay, all of them conserve energy, but some of them don't conserve charge, and some of them don't have this accuracy embedded in the integration of the orbit. So you really need to have all these things in order to get a solution that's actually good. We can now actually check order of convergence in time. It's second order, as it should. It's a second order method. And here I'm showing a shock wave, and I'm comparing the shock wave with what you get if you linearize. And remember, when people tried this in the 80s, they were linearizing these couplings, and they never really got it to work, and we couldn't either. So the fact that it's nonlinear and converge actually helps you to get these answers right. Okay, so I can solve this system. How fast can I solve it? Can I accelerate it? And what is the potential? So it turns out, these are fairly standard assumptions as to time steps you can use and discretization mesh sizes and that sort of thing. If you compute the CPU of the explicit time marching method that I showed earlier with the new implicit, there's tremendous potential for acceleration, provided that you actually don't iterate too often. Okay, if you take too many iterations, it stands to reason that the cost is going to go up, and then you're going to lose your advantage. This L over lambda debye, this is the smallest length scale that I mentioned earlier, so it could be a really large number, and it's actually to the power of the number of dimensions. So the potential is very large, but again, I need to have a good iterative method. Otherwise, it won't work. So what I'm trying to do is to minimize the number of iterations, and for that, I'm going to use a fluid model. And the idea is to essentially find a guess to the linear response. Remember that Newton is a linearized method. To the linear response of the fields based on some approximate model that's going to give me good enough answer that I can use it as an accelerator. Okay, so I postulate a fluid model. This comes from taking moments in velocity space of the Vlasov equation. Linearize it, because again, I'm solving a linearized problem. And what you see here in yellow is input. This is stuff that I know or that I can find out. And in blue here is the output, which is in this case the guess for the electric field. Turns out you can solve this system, and it actually gives you a really good guess for the solution. And we actually realize in simple problems significant acceleration based on this lambda debye, k lambda debye, which is equivalent to L over lambda debye in this formula, right? So we actually get the potential of several orders of magnitude acceleration for this system. We can also extend all this to electromagnetic. So I showed electrostatic, only electric field. We can do electromagnetic, and we can do multiple dimensions. And we inherit a number of really nice properties, including charge conservation, energy conservation. Momentum conservation is not exact. We cannot make it exact. Nobody knows how to make it exact. But we get comparable values to what the explicit integrator would do. And then you actually get in reduced dimensionality additional properties like canonical momenta conservation, if you care about that. And also the gauge, which in this case is a Darwin model, has to be divergence-free for the vector potential, is also conserved to very good accuracy. So we have a lot of constraints that we're satisfying by carefully discretizing and doing this implicit integration. Okay? We also are able to accelerate dramatically. This is an electromagnetic case where we do a study in terms of mass ratio of between ions and electrons. The larger it gets, the harder the problem is. And what you should look at is the comparison between the linear iterations, the GMRS iterations without preconditioning, fluid precondition, and with. And you see that there's a 2 orders of magnitude difference between having a preconditioner and not having a preconditioner. And if you wonder what this 0 means, it basically means the preconditioner is so good I don't even have to actually go into GMRS. It's just good enough that it says, okay, I'm done. I don't need to go into it. And similarly with mesh, okay, refinement, the finer the mesh, the harder the problem. You see that without a preconditioner, I get, significant growth of iterations. With preconditioning, I get that very much under control. So this is the impact of having a good preconditioner versus not. So it makes the difference between tractability and non-tractability. Okay, so this is all for, kind of idealized, simple problems, 2D maybe, but we're actually applying this right now to gyrokinetic formulations, which are the workhorse for simulating turbulence in tokamaks. And some of our colleagues here actually have worked in that area. Microturbulence is critical because it has a direct impact on particle energy confinement in tokamaks. And gyrokinetics, as I mentioned, is the workhorse. It exploits the fact that these particles are gyrating fast enough that you can average out that time scale. And it's really one of the most successful asymptotic models in magnetic fusion, okay? But the particle implementation of this model suffers from significant accuracy issues. One, it's typically semi-implicit. We already showed that semi-implicit may not be such a good idea. And two, actually features numerical instabilities that have been overlooked maybe, or misunderstood for a number of years until we actually got and looked into them. And again, the key is to reformulate your distribution function in a way that you can average over the fast scale, and what's gyrating so fast becomes a ring of charge that moves along a gyro center. And that now can actually go and gyro average the equations as well. And in doing so, you basically substantially ameliorate the time and length scale disparity that I showed earlier from the full Vlasov that I showed to the gyrokinetic, which is significantly more approachable. And that's why it's such a successful model. But it suffers from two critical problems because it's semi-implicit. One, cancellation errors. That's the fact that you're taking two terms and putting them at different points in time, also discretizing them on two different discretization bases. One the particles and the other one is the mesh. And as a consequence, these things don't cancel exactly. That leads to significant errors. The other one is finite grid instabilities, which are aliasing errors that come from the fact that particles are living in a continuum, whereas the fields live on a mesh, okay? These were thought not to exist in gyrokinetics. It turns out they do. And we showed that by analysis. With both of these can actually be significantly improved or removed completely with full implicit methods. And we have some preliminary data here, actually this is published, where we have really good, this is the number of iterations, by the way. This is the time step ratio and the number of iterations. And you can see the number of iterations is actually significantly well controlled, 3 or 4, for a really large variation in the beta of electrons, which is one of the critical parameters in the tokamak characterization. We also eliminated finite grid instabilities. This is a case of a nothing wave that just goes unstable as per theory. Whereas if we formulate this correctly and do it implicitly, we completely eliminate that instability. We actually get a fully stable wave just propagating through. Okay? And we've tested and verified this in magnetic fusion relevant problems. In this case, is in ITG KBM. It's one of the instabilities that happen in these devices driven by temperature gradients. All right. So this is part 1 of the talk. I think I have maybe 10 minutes. So I'll go and change subject now and go into inertial confinement fusion and some of the work we've done there. It's actually, the system of equations is the same, but the challenges are very different. So again, this is a small capsule that gets bathed by radiation and by the rocket effect compresses and ignites. That's the theory. At each point in radius, you have a description in velocity space that leads to this 6-dimensional probability distribution function that is described by what's called the Vlasov-Fokker-Planck equation. And that acceleration, it just comes from the electromagnetic field. And the collisions, what they do is they take something that looks as bad as you want it, and essentially renders that a Maxwellian in thermal equilibrium if you allow for enough time to pass. Okay, that's what collisions do, they thermalize. When it doesn't happen, when you don't get something to thermalize, then what happens is you start getting issues with the fluid models that people use to simulate the system. So this is a plot that is describing, my apologies, the ratio between the predicted and the experimental yield of a capsule as a function of the Knudsen number, which is the ratio of the mean free path to the system size. When this number is small, your fluid formulation is good because particles are colliding frequently enough. When this number is large, which large means in this case 10 to the minus 2, then this, then you can actually show that your fluid description starts losing fidelity. And what happens is the prediction of the models actually starts degrading significantly, right? So again, Vlasov-Fokker-Planck equation, but this collision operator, which I haven't gone into yet, is a very, very challenging beast to solve. So it's an advection diffusion equation in velocity space, if that means anything to you. The coefficients are actually Hessians and gradients of what's called Rosenbluth potentials. Those in turn are actually connected to the distribution functions through a Poisson equation. So this renders the system non-local in velocity space, which is very challenging to solve on a computer. Okay, and then that couples with Maxwell's equations, again through the moments. So it's very high dimensional, exceeding the multi scale as before. So what we did is actually consider reduced dimensionality, one dimension, just spherical or planar. In one dimension, you can actually describe the full velocity space with two dimensions, which is cylindrical, in this case, geometry. We took some asymptotic limits. We assumed it was quasi-neutral and bipolar. That eliminates some of the fastest time scales and length scales in the system. And then we consider, for now, fluid electrons and then kinetic ions. So we treated the species differently. And that's a pretty good approximation for what we cared for. So then the equations is the Vlasov-Fokker-Planck for the ions, plus a couple of equations for the fluid electrons, plus Ohm's law, which is really the electron equation of motion that gives us the electric field. If you look at this already simplified system, and you try to understand what kind of requirements you're going to need to solve this on a simple mesh, just assume you have uniform discretization and explicit time stepping, you very quickly arrive to something that's impossible. So the number of mesh points ends up being 10 to the 12, 10 to the 13 in 3 dimensions. And the number of time steps is 10 to the 10. That's what you would have to use in order to solve this problem on a naive discretization, on a naive mesh. You can't do this problem right now. So we went and looked at full implicit time stepping again. We actually used adaptivity as much as we could in velocity space as well as physical space. So the capsule is imploding, so the radius is changing. You should follow that. And also the species are either drifting or heating up, cooling down too, and you had better follow that with your mesh as well. So we implemented these as a map in our equations, so that analytically we transform our equations to include these transformations, so that then we end up having an equation that's described on a computational method that doesn't change. All the changes through the map. All right, and we did this so that we can conserve all the properties we wanted: mass, momentum, and energy, in particular. Okay, these strategies saved us 12 orders of magnitude in computational complexity. 12 orders of magnitude. So now something that was impossible is now possible. These are the formulations of the constraints that we want to solve. And in this case, what ends up happening is this is the transformed equation with all these maps, and these are Lagrange multipliers that we need to add in order to conserve those properties. These are nonlinear functions of the solution, and you need to iterate nonlinearly, but we're already doing that anyway. Okay? So that ends up being the system we solve. And now if we actually look at what we need, instead of 10 to the 12, 13, you get 10 to the 6, 10 to the 7 number of mesh points. And instead of 10 to the 10 time steps, you require 10 to the 3 and 10 to the 4. And these are actual numbers that we see today. And we can solve this on a cluster that's a reasonable cluster with a few thousand nodes. Okay. This is one example, simple relaxation problem. This is 0D, just in velocity space, multiple species, very different temperatures. A uniform mesh, because you have different species, would require, which means they have different mass, which means they have different thermal velocities, which means they expand very differently in velocity space, would require a mesh of 140,000 times 70,000. So very unreasonable. With our adaptivity, we do this problem on 1 to an 8 by 64. So that's a savings of 10 to the 6, a million times the computational complexity. So we couldn't do it, now we can. Why do we emphasize conservation so much? Because if we don't do it, we get the wrong answer. This is exactly the same simulation, exactly the same setup, exactly the same mesh, exactly the same time step. The only thing we have done is turn off conservation. That's all. Okay, so energy is not conserved anymore. This gives us a perfectly good answer that compares really well with the semi-analytical models that we know. And this just gives us something that goes into completely different path. It's non-physical at this point. So this is why conservation properties are so critical. We also accelerate these systems using moments, same as before. Very similarly before, we have this what we call high order system, which is the accurate high fidelity description with the Fokker-Planck. And the low order we have the moment equations that update things like density and momentum and energy. And then what we do is we iterate on this in a way that actually sort of separates the coupling terms without sacrificing performance. So we solve these low order systems, the moments, to find moments and fields, and then we feed those into the Fokker-Planck equation through the acceleration term to actually solve for the distribution function, and we iterate. And it turns out that if you do that right, it converges very quickly. All right. So what does it mean to do it right? Well, what do you get first? So this is convergence history. So this is number of iterations versus residual. So your error is decreasing. It decreases very well when your time step is, not too large. So delta t, new collision is the collision frequency. So if you're resolving the collision frequency, things go well. The moment you start stepping over your collision frequencies, you're trying to push over that fast time scale, then it doesn't converge at all. So this is not a very useful iterative method. With our fluid acceleration, you lose the sensitivity to this parameter, and now you can actually reliably converge regardless of what delta t is, your time step, okay, which is exactly what you want. This is an actual comparison to experiment with, this IFP is the code that implements this high fidelity model versus a fluid description. And as you can see, this is the field density of the capsule at the beginning. So the lesser the field density, the more kinetic the problem is, the less collisional it is, and therefore the more you expect things to matter, and they do. Okay, so our code is able to predict the right yield for these capsules for a much larger region than the fluid description would. So there's a benefit to do things with higher fidelity. And these are actual numbers coming from some of the simulations in terms of the number of degrees of freedom that we are able to save, and the number of time and how large our time step can be compared to the explicit time step you would have to use. And simulations typically take about a day on a few hundred cores. And that's it. So hopefully I convince you that the multi-scale implicit algorithms exploiting model hierarchies that are able to target the sources of problems actually can give really very highly performant algorithms that allow you to solve problems of interest. I have really not talked about a lot of the details under the hood, formulation, discretization, conservation strategies, other than just to mention how we do it, the solvers we use underneath to make sure that we scale, and so on and so forth. Throughout, asymptotic preservation is key. You need to have these models be consistent, and you need to have conservation properties for the key invariants that are going to matter, or else your solution is going to go to a place where it's not going to be physical. And therefore, you're going to get the wrong answer faster, which is never a good idea. And now we're applying this actually to both magnetic fusion and inertial fusion. So that's it.